So just now we mentioned the potential refraction, the potential refraction. Actually, it's just like if this kinetic energy is higher than the potential energy, then it still have some probability to be refract, and the ratio to be refract is this one, and can be calculated by this equation. And K and KB is nothing but K is this one, and then KB is this one. KB is this one. So, and you have some question, and then you just need to plug in or M, E, U, B, H bar, and then you can calculate K and KB, and then you can calculate the ratio, refractive ratio and transmission ratio. So for this case, it is another case which is called the barrier tunneling, 就是穿隧的效应。So a plug slides over the frictionless ice toward a hill. The plug's gravitational potential at the top of the hill will be UB. 那这个是那种冰像曲棍球那种球，那这个是一个冰的那个就是一个山丘那样，所以它冰的意思是假设说没有任何的阻力。那按照古典力学的话，那这个球啊，如果不够动能的话，它比如说滑到这里，它就会往回走。那量子力学的话就不一样，它可以穿过去，就是可以穿墙嘛，可以穿墙。So as the plug climbed the hill, kinetic energy K transfer into gravitational potential energy U. So if the plug reaches the top, its potential energy is UB. Thus the plug can pass over the top of only if it is initially mechanical energy. E is larger than UB. So hill acts as a potential energy barrier. 就是一个墙，能量的墙啊。So for short, a potential barrier. 所以这两个就是一个就是古典力学的话，你能量够，它好像看不到；你能量不够就会返回来。但是量子力学就不一样，能量够你还是可能会弹回来，你能量不够还是有可能穿过去。So here is another case. There is a potential barrier for the non-relativistic electron traveling along an ideal wire for electrical thickness. 所以说简单来说，你就是看到是几个 region. So you can see there are a few regions. So in the middle part, the potential energy is UB, which is this part. So between 0 and L, it is UB. And for other region, the potential energy is 0. So you can see this is V equals to 0. This is V equals to 0. This is VB equals is a negative amount. So similarly, this UB is E, this is negative, and then multiplied by VB, which is also negative. So this is a positive value. This is a positive value. So this time E has a smaller energy than UB, but it will have some probability to go through this potential wall. And it is related to the thickness. Of this wall, which is defined to be L. So something astounding can be happen to the electron when E is smaller than UB. E is smaller than UB. So since it's a matter wave, the electron has a finite probability of leaking. Finite probability of leaking or tunneling. 这个叫做串隧效应，就是 英文叫做 tunneling effect。tunneling effect. So the wave function phi x describing the electron can be found by solving the Schrödinger's equation separate for three regions: to the left of the barrier, within the barrier, and to the right of the barrier. So it's similar to solving the case for the refraction, and actually we can just, this one is the Schrödinger's equation, and then for region 1, u is equal to 0, so we have this solution. And then similarly for region 3, which is x is larger than L, u is also 0, k is this one, and then this one maybe go back, so we have both terms. But for region 3, it can only go to the right side, so we only have this term. And for region 2, this is region 2, this is UB, and now we have UB smaller than, UB is larger than E, E is smaller than UB. So you can see that this one will look like d squared phi dx squared minus 2m UB minus E, and then over h bar square phi to be 0. Because now we have a UB is larger than E. For the previous case, E is larger than UB. So we make this term to be larger than 0, and then we have a minus sign here. So now we define B to be this way. So for this case, K, for this way, K is still the same, but now we do not have KB, which is not a plane wave. Now it is exponentially decay. Because this one is a negative sign. So now we have a d squared phi dx squared minus b squared phi equals to 0. So you have s squared minus b squared equals to 0, and then s equals to plus or minus b, not jb. So here we have these two exponential terms. And similarly, we can just use the boundary condition. The boundary condition. Because we have phi 1, phi 2, phi 3, and actually we should have phi 1 0 should be equals to phi 2 0, and then phi 2 L should be equals to phi 3 L, and then also phi 1 prime 0 equals to phi 2 prime 0, and then also phi 2 prime L equals to phi 3 pi L. Similar to that, you can just solve the relationship between A, B, C, D, and E. And then finally, you will find that this is a solution for phi x, and this graph shows the absolute value of the wave function, and then take the square, which is the probability. So on the left side, it is like a sine wave. It is actually a standing wave. 驻波 standing wave. And then for the middle part, it will be exponentially decay. And then because this one is one side, so it's like a plane wave again. So on the left side, standing wave. This side is plane wave. This one is exponentially decay. Exponentially decay. So it depends on this value. This value define how fast it will decay. If E is smaller than UB but close to it, then this value will be small, and then it will decay slower, and then it will have a larger probability to go through. But if E is much smaller than UB, then this term will be large, and then it will decay fast enough. And it also depends on how thick this wall is. If this wall is thin enough, it will have small probability to go through. So you can imagine now the CMOS technology, like so you have the MOS transistor like this. Maybe for this one is a PMOS. So this is P substrate, P substrate. So this is N plus, this is N plus. So this is the oxide, this is the polysilicon, and then this is the channel length. Now we talk about tens of a nanometer or even smaller. So if you realize it is a potential wall here, So maybe this. So if you like, oh, this is a potential wall, but the electron will still able to go through. So it's still like the leakage voltage. But if this wall is thick enough, then the leakage will not be so probable. And that's why it will be even more and more challenging to design the chip in advanced technology. Yeah, so the calculation in between this stuff is omitted because it is a bit too complicated. But actually, this T will be look like this way, and it can be approximate like this. Although you feel like, oh, this one is like this way, but you can imagine this term should be quite small. Although it is not 0, but C should be much smaller. Otherwise, it will be going up, but it doesn't really make sense. So in that case, it can be approximate as only have the term D. And in that case, we try to calculate the probability at here and at here and take the ratio. So actually, the portion for the electron to be transmit is like this one. And actually is this term. So it is related to the thickness of this wall, and also B is related to UB minus E. So if the kinetic energy is close to it, then this term will be larger, because as long as B and L should be positive, which means that this exponent should be negative. And the largest case is e to the minus 0, then it will be 1. And for B and L to be larger, then this term will be smaller and smaller. So this is about the called the barrier tunneling, the scanning tunneling microscope. 所以这个是所谓的串穗显微镜。那就是你如果足够大的东西，我们用肉眼看；那比较小的东西，我们可能拿个放大镜。那你们什么生物实验，可能看个细胞，可能拿个显微镜，那就是使用到透镜的那些东西，那就是一个加强版的放大镜嘛。那再下去的话，你如果要看到原子尺度的那种很小的那种形状的话，那这个就是透过这个 tunneling effect 做这个串穗式显微镜。那它就是它就是有一个 potential wall 的东西，然后它就贴着那个去旁，然后它如果有起伏的话，它就要跟着它去动的话，你才能够有维持着同一个串穗的电流。那用这种方式，然后去用一个很微小的控制你的这一个电极跟你要测量的那个物体之间的距离，然后去保持着那个圈穗的电流大概是多大。那用这个去看到一个立体的形状，所以这个是一种应用啊。那这里有一个 sample problem。Okay. So suppose that electron have a total energy 5.1 eV, approaches a barrier of height UB. So and the thickness L is 750 picometer. So what is the approximate probability that the electron will be transmitted through the barrier to appear on the other side and detectable? Maybe there is a detector here. So on the other side of the barrier. So yeah. So actually we only need to substitute all the values into the equation. 2m ub minus e, and then over h bar, take the square root. So it is nothing but, so this is a electron, so 2 times 9.11 times 10 to minus 31. And then ub is 6.8, and then e is 5.1. Both of them are eV, so multiply by 1.6 times 10 to minus 19, and then take the square root. And then h bar is 6.63 times 10 to minus 34 over 2 pi. So B is 6.67 times 10 to 9 meter inverse. So this is B, and you should be noted that because we should have a equation like exponential to minus 2BL, and this one should be dimensionless. 它应该是没有那个量纲的 dimensionless。两杠，它是 dimensionless 的，也就是说这个 L 的 dimension 是长度嘛，所以这个应该是长度分之一。好，所以这个是长度分之一。然后so it asks you about what is the approximate probability. So we can use t equals to exponential to minus 2BL. So it is exponential to minus 2 times 6.67 times 10 to the 9th power. And then L is 750 times 10 to minus 12. So this one is 75 times 10 to minus 6, which is a very, very small probability. Which means that suppose you should have, maybe you have 45 times, maybe you have 1 over 45 times 6 electron. And then on average, there will be 1 electron going through this potential barrier. On average, because probability doesn't mean exactly what it will happen, how many times it will happen. So for the next one, what is the approximate probability that the proton with the same total energy, this is B, so will transmit through the barrier to appear on the other side. Proton, oh yeah, proton. This one is proton, not a electron anymore. But actually, you know that proton has the same amount of charge, but the mass is much heavier. It's much heavier. For electron, the mass is 9.11 times 10 to minus 31. For proton, the mass is 1.67 times 10 to minus 27 kilogram. So for this case, B is 2 times 1.67 times 10 to minus 27. And then this term is the same, 6.8 minus 5.1. And then times 1.6 times 10 to minus 19. Take the square root, and then here 6.63 times 10 to minus 34 over 2 pi. So this is B for the proton case. We put a P. So for this case, B is 2.86 times 10 to the 11th power meter inverse. And T would be exponential to minus 2 BPL. So exponential to minus 2 times 2.86 times 10 to 11. And then this one is 750 times 10 to minus 12. So in this case, T is 8.3 times 10 to minus 187。这个几率就更小，小很多。这个是-6，-6的话还蛮大可能的，因为比如说你有一安培，那可能这个已经有45个 μA 是会穿过去哦，这个就很小。这个我不确定要被雷劈到多少次，连续被雷劈到多少次才是这个几率了。可能要连续被劈，不知道18次还是9次啊，我不确定被雷劈到的几率是多少。Okay. So this one tells you that if it is lighter or smaller electron, there will be larger probability to have the quantum effect. But not absolutely. But actually, for the same setting, the electron have this probability to have the tunneling effect, but for the same setting, the proton has a much less probability to have the tunneling effect, but it's still not zero, although it's really small.